right? We remember this, correct? Okay, perfect. So can anyone give us the answer for a minus b squared? Perfect, thank you very much. And finally for this. Very good, excellent. So forgive me if I insulted you with this, sorry. So this is the difference of squares. I just want to make sure that from now on, moving forward, no one will ever ask, how did you come up with this 2? Right? Or how did you come up with this 2? Moving forward, is that clear? Because there are 2 terms that are the same and we combine them. Combine like terms. That's where the 2 is coming from. And what I highly recommend is remembering this as a general. Today is the 27th, right? All day? Okay, so we know that a plus b, everything squared, is a squared plus 2ab plus b squared. But this is for a and b. So if I want in general first term plus second term, everything squared. Now this is where we come in. This is where we say, okay, how do I remember this? Oh, it's very easy. It's the first term squared plus 2 times the first times the second plus the second term squared. Now, if it's easier for you to remember it with a and b, it's fine. But it doesn't necessarily mean that the first term will always be a and the second term will always be b. We know that. So in general, this translates into first term squared plus 2 multiplied by the first term multiplied by the second term plus the second term squared. And this is only one term, one quantity, one product, one term. Okay, so just a quick example. How will I square, let's say, 2x squared minus 3y to the 4th? How many terms will you give? 3 terms. You will square the first term. Oh, if it's minus here, then it's minus here. So will you square the first term for me? Good. Minus, let's write it out. Minus 2 multiplied by 2x squared multiplied by 3y to the 4th and plus 9y to the, very good. And of course I have to take care of this. So it's 4x to the 4th minus 2 times 2 times 3 is 12. X squared y to the 4th plus 9y to the 8th. Is this okay? Do we remember this? Do we have any questions? Any questions on this? Okay. So, yes, any questions? Okay. So that's my first page. This is my second. Okay, so let's go back here. So is there anything that you would like to see from 1, 2, and 3? As a quick review. Is there anything that you would like to see from 1, 2, or 3? E on number 2, this one. Very good. So this is what type of polynomial? It doesn't have a name. It's a polynomial. But how many terms does it have? 4. What is the only factoring method that we could think of when it comes to 4 terms? By grouping. Very good. So the method is factor by grouping. Perfect. Okay, so I'm going to group the first 2 and the last 2. If it doesn't work, I will not conclude that it's not factorable. I will group the first with the third and the second with the 4th. I will not conclude if that doesn't work. I will not conclude that it's not factorable. I will also try the first with the last and the middle 2. And only then, if that doesn't work as well, then I'll say it's not factorable. So let's try exactly the way it is. X cubed minus 7x squared minus 4x plus 28. So if we factor something out of the first two, we will factor out x squared, and what is left in parentheses? What should I have coming out from the other two? Otherwise, I can continue, and I will have to regroup. What should I have coming out from the other two? Otherwise, I can't continue. Must be x minus 7. And only then I look. Only after I write x minus 7 in parentheses, only then I look and see. I cannot fabricate anything. If it's not there, it's not there. But I must write it first. If I don't write it first, I may put plus in here. Who knows whatever I'm coming up with, right? So now I look. So what do I put in front so for this to work and be legit? What times x is negative 4x, and what times negative 7 is positive 28? Minus 4 indeed. So now I continue factoring out the greatest common factor. I have two terms now. This is one term, one product. And this is one term, one product. And now I factor out the greatest common factor from these two, which is, and then it happens that I have x squared minus 4, and I have to continue because this, I can use the difference of squares. That's the reason why I wanted to refresh your memory on this. Because of two reasons. First, going from your right to your left, but what is important is going from your right and factoring. This is expanding, going from your left to your right, and this is factoring, going from your right to your left. So I'm using this, but going backwards. So what do I have? Paul, you want to say something?
No.
Oh.
X plus 2 times x minus 2 times x minus 7.
Perfect. This is the complete factor form. And you could say, why do I need this? Well, we already know. We're going to use this a lot in limits. In limits, differentiating and integration and so on and so forth. So factor is very important. Okay. Anything else? C from number 3. That's a linear equation. Are you sure? That's okay. No, because maybe you just caught his eye because of fractions. Okay, this is a linear equation. There is no x in the denominator, right? There is no square root. There is no absolute value, so this is linear. What do you recommend? Right. Well, of course, I should, you can, instead of multiplying 4 terms, you can move 3 to the other side. So you have negative 3/5 equals 1/2 x minus 8. And then multiply both sides by the least common denominator to eliminate fractions. And in this case, the least common denominator would be 10. So stop me anytime. Remember, the ball is in your court. If you have questions, if something is not clear, always stop me. Okay? So when I multiply this by 10, what do I get? Awesome. When I multiply this by 10, and when I multiply this by 10, good. So I move 5x to the other side. I get negative 11x equals negative 80. And of course, x would be, that's okay, x would be 80 over 11. Any questions on this problem? Anything else from 3, or we move on to 4? Now 4 extends on the other page, on the back. So I have 5 functions here and 2 here. So let me know if you want to choose anything from there. E on number 4. This one, the cube root of x. Very good. The reason I'm doing this is not to scare you and say, oh, I don't know this, I should drop the class. No. What I'm saying is, this should have been known if you say I don't know it. I'm going to get help right here, right now, okay? So that's the reason for this. And I want you to do a little bit of research and come up with the rest. So we're asked to graph a function that is the cube root of 4, oops, the cube root of x plus 4, is it? Yes, sorry. Now, I'm going to say this now, and hopefully you're going to understand or remember that any time you're asking me to graph a function, my very first thought must be the, no, if I want to use transformations, yes, but let's say I don't want to use transformation. Joe is right. He said, okay, look at transformation. This is very easy. There's nothing to do here. Just use the cube root of x, graph it, and then move the graph up 4. We're done. However, my question is, whatever you're asking me to graph, what has to be my first thought? Okay, I want to travel to New York. I'm gonna go to BWI and fly to New York. What is my first thought? What do I need?
A ticket.
Right. And in order to get a ticket, what do I need?
Money.
Right. So it's the input. If I don't know the input, I don't know what to plug in. So what am I discussing here?
Domain.
Exactly. So my first thought, every time you ask me to graph a function, must be the domain. I must ask myself, where does this function exist, and what I can plug in x? Because if you're asking me to graph the square root of x, I would have to say, well, I cannot plug in -4. Right? Because the square root of -4 is not a real number. So that is my first thought. And this will be throughout the entire semester. You have to remember that every time we graph a function, our first thought must be the domain. So now, once I establish the domain, my second step is I have to show my work, and I have to come up with a chart or a table of values, or the pairs, x and then determine y, input and then the output. So can anyone give us the domain of this function and why? So my question to myself is this. What can I take the cube root of? Can I take the cube root from 0? Yeah. Can I take the cube root of -8? Yeah, it's -2. Can I take the cube root of 8? Yes, it's 2. So what is the domain of this function? Very important. All real numbers. And my second step has to be a table of values. Horizontal, vertical, whatever type of ordered pair of chart you want to use. I don't mind. But I have to present my work. And here's my work. It goes from -infinity to infinity. And yes, from here on, it's all straightforward. I'm going to choose convenient numbers. I'm not going to choose 7 because I'm going to have some difficulty with taking the cube root of 7. Of course, I'm going to use -8, -1, 1, and 8 and 0. So when I plug in -8, I will get +4.
2.
Good. When I plug in -1, right? The cube root of -1 is 1. 1 plus -1 plus 4 is 3. When I plug in 0, 4. When I plug in 1, 5, and so on and so forth. And here I have 6. Now, obviously, I know that this function exists for any real number. I know how to graph the cube root of x, right? So this is the square root of x, but the cube root of x is this. And I have not hit any negative values. So I should go further to the left. Or, as Joey suggested, he's very smart, he said just use transformations on this function. Just graph. So I should come back here and hit some negative values. So graphing the cube root of x. It's a very important graph. You will see later on what we're going to study and what this is so special. And we're going to shift the graph up 4. So 1, 2, 3, 4. So that is the cube root of x plus 4. It's not a perfect graph. Every time I use transformation, it's not a perfect graph because I did not determine the x-intercept. I have the y-intercept. It's definitely 0, 4, no question. But I did not determine the x-intercept. I can determine it by simply saying the cube root of x plus 4 must be, so that's for the x-intercept. Yes, awesome. And I move forward to the other side. What type of equation am I solving now? If it has a fraction and x in the denominator, it's rational. If it has the absolute value in it, it's the absolute value. But this one has a radical in it, so it must be radical. A radical equation. So my question is, how do I solve it? I need a cure that undoes the cube root. Exactly. That's the only cure. If you want to remove the cube root, you have to cube. If you want to remove the cube, you have to take the cube root on both sides. So that's why I have x equals negative 64. That's why I didn't get this. So I have to plug in here negative 64 to get the 0. So it was way out of my coordinate system. But I can easily determine it. So the x-intercept is negative 64, 0. The y-intercept is 0, 4. Any questions on this? Any questions on this? Okay, so let's go to the next page. Graphing of a piecewise defined function has a big role in this class. Being able to read from the graph of a piecewise defined function, being able to determine limits, left and right. I'll explain that later. So this is extremely important. This you should have no difficulties with to do it at home. This we can do in class because it's finding the difference quotient for a rational function, 1 over x. So, and here we'll see. Okay, ready? So what would you like to continue with? Good. Let's do it. And I think I'm on page 3. So we have a function f of x, which is 2 for x less than or equal to 0, 1 minus x squared for 0 to 2, and the square root of x plus 5 for x greater than or equal to 4. When asked to graph this function, what is the first thing that I need to do? What is my first thought, without which I can't start? I can go to the BWI, I can smile nicely, but I can't get on the plane if I don't have money. Domain. So, although I did get into a concert twice with no ticket. It was a long time ago. And it was La Traviata, and I had to see it, and I didn't have $80 to pay for it. And they did allow me to come in. I don't know how, but they did. Twice in a row. Okay, but I was young and silly, and I tried, and it worked. Okay, so I have to find the domain. So I look at this, and let's change it into interval notation. Negative infinity to 0. Good, perfect. Let's change this one into interval notation. Very good, 0 to 2. And finally, let's change this one in interval notation. I'm not saying that you cannot identify the domain if you don't do this. I'm only saying that this will help me in the next step I want to show you. Okay? So I have everything from negative to 0, including 0. I have everything between 0 and 2. I do not have 2. 2 is nowhere to be found. There is a gap till I get to 4, and 4 to infinity is there. So what is the domain then?
Negative
-infinity to 2, open, very good, union 4 to infinity. This is what I have to present in my table. Nothing else. I cannot put anything else in the table. So here's my x. Here's my f of x, negative infinity. 2, I have to have 0 in the chart no matter what. 2, 4, infinity. An open parenthesis right under 2, a closed bracket right under 4, nothing in between 2 and 4, a bracket facing left under 0, and a parenthesis facing right, also under 0, touching. Why do they have to touch? It's because sometimes you will see there will be a parenthesis here, and a different number inside. But once they're touching, there is no additional situation in there. Okay, so is this setup clear so far? Please ask questions, don't be shy. Because if you have a question, possibly other students have the same question. So you're helping me. Many times in the past, and I do remember one time, even Joey was last semester, he said, what was the question that he asked me? You're saying something, there was a connection between, what was it? Do you remember? I know. And I said, how beautiful, such a question. And I inserted that in my notes, but I can't recall exactly what it was. Was it on odd and even something? The symmetry? Okay, yeah. I like to think about that again. So, yeah, he said, is this connected to that? And I said, oh, yes. Thank you for asking, because I would have never connected it myself. But he was right. He's always right. Okay, so negative infinity to 0, bracket to the left of 0. As you see it, it's facing this way. Parenthesis to the right-hand side of 0, right under 0. And then 2, parenthesis facing this way. Nothing in between. This does not exist. I cannot have a graph here. Okay? And then 4, bracket facing this way and to infinity. Is this okay? Okay. So now I know that this is going to be an overkill, but I would like you to give me the branch, the piece of function that I would be using for any x values between negative infinity and 0. Just read it to me so I can put it and have it right here under my nose. Indeed. So which function will I be using between 0 and 2? For any x value between 0 and 2, there is one particular function and only one. And for the last one? Perfect. Thank you, Paul. So now, in your alley, right? Okay, perfect. So now, here's the question to myself. This is a linear function. This is a quadratic function, and this is a right. So this is already complex, right? I have 3 different pieces, 3 different things to graph, and I have to know how to graph it. Good. So for 2, right in here, this is linear. I'm going to pick a number. This is -1. When x is -1, how much is y? Of course. When x is 0, how much is y? And I put it right in here, inside the bracket. On the other side, I want to plug in 0. And you should be opposed, right? Say, no, you cannot plug in 0, right? 0 is not here, right? But I have to plug it in. If I don't plug in 0, I have to plug in 0.00000000001. Because I have to start as close as possible to 0. Instead, I'm going to start with 0 and leave it open. If these 2 numbers are not the same, if this happens to be 2, then it's a full point. But if this happens to be 5, it's not a full point. It's an open point, 0, 5. So please plug in 0. Tell me what we have on the right-hand side of 0. 1. They're not the same. The point 0, 2 would be a full point. And the point 0, 1 would be open. On the same vertical, for the same x value, it will look like this. So 0, 2 and 0, 1 for the same x value. This does not mean that it's not a function, because the value is here, not here. Right? It's not continuous, correct. Okay, so now let's plug in 2. -3 indeed. Let's plug in 4. Good. Let's plug in, what else? If I have 5 plus 5 is 10. So I need 16. So 9. I'm sorry, 11. Thank you. I need 16. So 11 plus 5 is 16. The square root of 16 is 4. And that's good enough. Do we understand that we had to have some ordered pairs in each and every branch? Now, if you graph something like this, one branch over the other, I can't give credit. Do you understand there are 3 different functions and they cannot overlap? This is not a function, right? By the vertical line test, this is not a function. So for -∞ to 0, you're going to have one graph. For 0 to 2, a different graph. And for 4 to infinity, a third graph. But they will not touch. They will not overlap. Okay? Ready? Okay. So I start from left to right. And I start with -1, 2, which is this point. Then 0, 2, which is this point. And it is a full point. Why? Because it's a bracket here. And now I'm ready to graph. It's a horizontal line, a linear function, y equals 2. Only between -∞ and 0. Now, 0, 1 is not a full point. It will not be a function if I put a full point in there. So 0, 1 is open. 2, -3, 1, 2, 1, 2, -3. This is also an open point. But now I have to think. Because this is a quadratic function, because the leading coefficient is negative, does it have a minimum or does it have a maximum? Perfect. So I have not determined the x-intercept, which I should, because I already know it's 1. When x is 1, the y value is 0. So I should always look for the x and y intercepts if they exist. Always. They are very important points. So then I have a point here, and I know it has a maximum, and here's my graph. And that's the middle piece. Now, the final piece is 4, 3. This was 2, 3, 4, 3. It's a full point. And I hope you agree with me. Well, 11 is somewhere, and I'm just going to graph it. Yeah, sometimes I become lazy. Sorry. So now this is the graph. We're going to do a lot with something like this in limits. A lot. So we have to be able to read from such a graph. We have to be able to find the domain, and then we're going to write the range in a minute. And we have to be able to graph a piecewise defined function. Okay, yes, please.
Are you a tough grader for your graphs? Do you have to label all the intercepts?
No, as long as I see the chart, you may say, I don't like your chart. I'm going to use my own. That's fine. I'm fine. As long as you present a chart that matches your graph. Because I'm not testing you on knowing how to, if you know how to use a graphing algorithm, punching in numbers. So if I see an analysis, because I'll explain why. In this class, I'm going to add to this chart 2 more. So I'm not taking credits. I was taught like this, and I think it's a fabulous method. But again, you may find something easier for you. So I'm fine with that. But in this class, I'm going to add 2 more rows here to this specific chart. That's why at least try to understand it if you don't want to use it. But you have to present your work and you have to show me how from whatever table you came up with this. So here's what this is very important. And I'm going to analyze it with you just for 1 minute. What do I see here? Because this is chapter 2. So from this point on is something that you may have seen before or not, but is not a prerequisite for this class. So this is, for most of you, should be new. Okay, here's how I analyze this graph. At x, as x gets closer and closer to 0 from the left-hand side of 0, the function values get closer and closer to 2. One more time. As x gets closer and closer to 0, the function values get closer and closer to 2 from the left-hand side of 0. From the right-hand side of 0, as x gets closer and closer to 0 from the right, the function values get closer and closer to 1. 1 doesn't have to exist in there, and it doesn't. But the function values tend to get closer and closer to 1. They are 0.9999999999999. They are getting closer and closer to 1. Okay, now, on this side there is nothing. On this side there is nothing. I cannot say as x approaches 2 from the right, I mean, there is no graph in here, but I can say that as x approaches 2 from the left, the function values get closer and closer to -4. -3, sorry. Now on this side, as x gets closer and closer to 4, the function values get closer and closer to 3. This is the concept of chapter 3, actually. This really means limit from left and right. So what can you say here? I'm going to come back to this with many examples. What can you say here? If from one side, the function value of 0, the function values approach 2, and from the other side, the function values approach 1. If I say from either side, what would you say? The answer is? It does not exist. Exactly. So from the left is 2. From the right is 1. From either side, it does not exist. Okay? So here, we only have the right side. So don't get upset about that or think too much about it because we're going to discuss this over and over. Okay, so I want to establish the range for this function and we'll move on. We still have a few minutes, yeah, half an hour. So what is the range? Careful now, very careful, because I have to start, I imagine that I cross this graph with horizontal lines. If there is a gap, I have to identify it. If there is no gap, then the function exists. So anyone from, with a parenthesis, exactly, from -3, comma,
To infinity.
careful, careful, let's do it slowly. It exists, it exists, it exists, it exists, yes, indeed, to 1, union, it cannot be bracket because it's just one value. I cannot put a bracket, I cannot put a parenthesis. If it's just one value or two values, finite, in other words, I can count them. I cannot count the values between 4 and 19 and 11. Right? But here I can count. It's just 2. If I can count them, it has to be with braces. Union what? Union 3 with a bracket, infinity. This is the range of this function. Good. Any questions? Any questions? I do want to remind you, I'm sorry, and I hope you remember this function, super important function, the arctangent. So I'd like to graph that quickly. because it will come back over and over, over and over. So y equals arc tangent x, but I will also graph y1, which is tangent x. So I'm kindly asking you to play with these two functions so you can get them embedded in your system. And you can say, wait a minute, what are you showing here? You're showing something and you're contradicting yourself with 5 minutes ago, right? Which you just did. You said domain first. You're just going ahead. True. So that's the reason, because this is a base function. There is nothing to it. But let's talk about the domain. The domain of, first I will start with tangent x. The domain of tangent x is negative pi over 2 to pi over 2 without negative pi over 2 and pi over 2. And these are the vertical asymptotes. So the reason why I went directly to this is because it's a base function. It's among the list of functions that we should remember. So this is very important. And here's the graph. So first, this is x equals negative pi over 2, this vertical asymptote. And this is the other one, x equals pi over 2. And here is the graph. Not to be confused with x cubed. So this is y1 tangent x. It looks like x cubed if you want to use comparison, but x cubed does not have vertical asymptotes. It's a polynomial function that exists everywhere. So x cubed will be something like this. And this one has vertical asymptotes. Arctangent is the inverse of this function. So all I have to do is reverse the vertical asymptotes into horizontal asymptotes and just graph a symmetric function with respect to the origin. So this is now y equals pi over 2. And this is now y equals negative pi over 2.
That's for the arctangent.
It's for the arctangent.
Okay.
So this is this graph, y1. And now I'm going to graph arctangent. Yes. And here is arctangent. Completely symmetric. Although, to be exact, the axes don't have the exact same units. But so this is y equals arc tangent x. Please remember these two functions. Yes, Paul?
Is arctangent the same as cotangent?
No, it's tangent inverse.
Okay, the inverse. Okay.
Tangent inverse. The same. It's different notation. So arc tangent x is tangent inverse, which does not mean 1 over tangent,
Right.
which means the inverse function of tangent. So please remember, commit this to memory, these two functions. One has vertical asymptotes, the other one has horizontal asymptotes, and they are inverses of each other. So if you want to say arctangent of tangent inverse and tangent inverse of arctangent, you will get just x under certain conditions, of course. Okay. So now we are easing into what I'm trying to do today. So let's work on this and simplify it. And then I'm going to ask you to use more functions. And then I can let you work on this, or we can select a problem next time from solving trig equations. So let's play with 1 over x plus h squared minus 1 over x squared divided by h. I'll explain where this comes from, but right now I would like to simplify it. I would like to simplify this fully. And then I'll explain where it's coming from. Okay, so I'm looking at this. The first step is to always try to analyze what you're given and think. So I'm looking at this and I see lots of fractions. I see this, and I see a subtraction of 2 fractions. So this is called a complex rational expression. Why is it complex? Because I have operations with fractions at the top, and also another fraction that is involved in there. Okay, so what I have to do is find what at the top? The least common denominator, simplify all this, put h over 1 and then flip it and multiply it, right? Okay, so let's find the least common denominator at the top. X squared plus.
I mean, it should just be both multiplied.
Of course, they have nothing in common. Of course. It's like adding 1/2 to 1/3. The least common denominator must be 6. 2 and 3 have nothing in common. X squared and x plus h squared, they have nothing in common. The least common denominator must be their product. No question. One reminder, we never multiply these. The factors in the denominator have to stay as factors. Do not waste your time and energy expanding x plus h. By the way, how many terms will you get when you expand x plus h? 3. Of course, we just did that an hour ago, right? It will be x squared plus 2xh plus, see, that's why I need it, right? So do not do that. Do not expand the factors in the denominator. We have to expand them when they're at the top so we can combine like terms. But in the denominator, do not touch those. Okay, so now, what do I need at the top of this? Of course. And what do I need at the top of this?
X plus h.
Okay, so exactly what it does not have, right? So this quantity was multiplied by x squared to get this, and this quantity was multiplied by x plus h squared to get this. So exactly what they don't have. Now this is clear, but this I have to expand. Be careful because you expand it and then you distribute -1 to all terms. You can't pick and choose. So I'm ready when you're ready for the top.
X squared.
X cubed.
How do we get the x cubed?
X squared times x. X cubed.
It's times 1. I see. It's times 1. Okay.
I'm looking at the bottom.
That's okay. That's okay.
Plus.
All right. Minus x minus 2x minus 8.
Awesome, Ellie. Thank you. Good. So that's perfect so far. What do you think is going to happen next? Which ones? Yes. Which terms? Very good. Would you be tempted? Would you be tempted to simplify this x squared with this x squared? Please say no. Thank you. So now at the top, I have to copy. I will copy this fraction, and I will multiply it by this fraction flipped, because that's how we divide fractions. But I see that the top has a common factor, and I don't want to write it twice. Can you? Yes. You can if you want to. So what do I pull out? -h. Very good. Awesome. And the denominator, do not touch the denominator. Don't do anything to it, please. Ever. So now please tell me what we have left at the top in parentheses after we factor out -h. 2x plus h. Do we all agree? Let's check. -h times 2x is that. -h times h is that. Perfect. What do you think I'm going to do next? Indeed. And the final simplified and no form, and no one can do anything anymore, is this. Any questions? Any questions? So now I would like to talk about where does this come from and why and what it represents. That's my page 5. difference quotient. So let's say we are looking at a function, the graph of a function. Here it is, function f of x. Let's say this is a distance function. And let's suppose I am asked to find the instantaneous velocity at this point. I'm going to call it point P. What do I have here? Thank you. Right? Clear? Perfect. So let's suppose I'm asked to find the instantaneous velocity at this point. I'm not asked to find the average velocity between 2 points. I'm asked to find the instantaneous velocity at that point. What is the instantaneous velocity at this point? Or rate of change. So what is the instantaneous velocity or the rate of change of function f of x at p? What would that be? Well, it gives us how fast the distance is changing with respect to time if the function f is distance. If this is distance, then I have time here and distance here. And if I want to determine the instantaneous velocity at this point, I'm really asked to determine how fast the distance is changing with respect to time at that particular instant, right? So if I throw this like on a parabolic or or a quadratic form, you're gonna ask me what was the speed here when my marker was here. Oh well, my marker doesn't have a speedometer, right? I can't tell you what is the speed there. But if I have this function, right, that represented the trajectory, right? Now let's say this is the distance function. If it's a distance function, then I will be able to find a rate of change, a second, 2 seconds after I throw it up in the air. So it will be the rate of change of distance with respect to time. Okay, now how do I do that? Well, the rate of change of this function with respect to time will at this point will be nothing else but the tangent, the slope of the tangent line. The slope of the tangent line at this point will give us the instantaneous velocity or the rate of change of the function at that point. If I manage to determine the slope, so this is the slope of the tangent line at P. All these mean the same thing. So the slope of this line, the instantaneous rate of change, and the instantaneous velocity are all the same. But the question is now, how do I determine the slope of this line? So find m of the tangent at P. I want to find the slope of the tangent line at P. How do I find that? I don't have a formula. I don't have an algebraic formula for this. I don't, right? The only algebraic formula that I know is y minus y1 equals the slope times x minus x1. This is the point slope form. And I do have one more that is, right, if you want, y equals mx plus b. This is to determine also the equation of the line. Or what I'm really interested in is the slope being y2 minus y1 over x2 minus x1. So this is what I'm after. But I just wanted to remind you all these three together. But this is what I need. In order to find the slope of that line, I need 2 points. Algebraically, I need 2 points to find the rise and the run. So this is the tangent line. I need to find the rise and I need to find the run with this formula. But I only have 1 point. So here's what we're going to do. I'm back to the same graph, back to f of x, back to p, which is x comma f of x. Of course, back to x, and back to f of x. I'm going to create a point. Going to create another point, and this will be point Q. And I am going to say that point Q is extremely close to P. And you can say, how on earth can this be extremely close? Well, imagine that I zoomed in. But it's extremely close. This point is really right here. But I have to zoom in so I can explain what I'm doing. So this coordinate will be x plus a little bit. We call the little bit, well, you know the little bit by h. So this distance is almost invisible to the naked eye. So this distance is a little bit. So tiny that we cannot see it with the naked eye. Very small. Yes, Paul always does that to me. I remember now. So can anyone give us the coordinates of Q?
X plus h.
X, comma. I'm sorry. X plus h, comma. I was way ahead of.
Function of
F of x plus h. Awesome. Now I'm going to determine the slope of this line, which is not a tangent line. Although Q is very close to P, this is not a tangent line. What is it? It's called a secant line.
I have a question.
Yes.
Why is the y value f of x plus h? Just kidding, never mind, I figured out.
Okay, so if this is 1,
Yeah.
this is f of 1.
Yes.
If this is 5,
Mhm.
this is
What? F of 5? Oh, yeah, okay.
better?
Yes.
Perfect. Okay, so now this is no longer a line that will give us the slope of the tangent line. It's not. It's not the rate of change, the instantaneous rate of change, or the instantaneous velocity at p. It's not. We agree on that. Okay, but now I have 2 points. And now I can determine the slope of this line. So I have the slope of PQ. Can anyone dictate the slope of PQ? You can say, and I will agree, you deviated from the problem. Not really. But it looks like it. So instead of determining the slope of the tangent line, I created a secant line, and I'll show you how I get to the tangent line in a minute.
Would be f of x, f of x plus 12 minus f of x over x. Did I say minus or plus? X minus x plus h. Perfect.
So y2 minus y1 over x2 minus
X
x1.
plus h minus x.
Very good. So again, this is not instantaneous velocity or the instantaneous rate of change, but it's the average rate of change between these 2 points. Okay. So we call this the average rate of change. Of course, I'm going to simplify. And I'm going to write that f of x plus h minus f of x divided by h.
So tangent is the instantaneous velocity.
The slope of the tangent.
The slope of the tangent.
Slope of the tangent, rise over 1.
Okay.
The rise over run is the instantaneous velocity and also the instantaneous rate of change at that point, and also the slope of the tangent, all three. Slope of the tangent, instantaneous rate of change, or instantaneous velocity, depending on what the function is all about. Good, so now let's go back to our quiz, readiness quiz, and let's compare. So I'm comparing this to this. For which function? 1 over x squared. Yes? 1 over x squared. So this is 1 over x squared, and this is definitely 1 over x plus h, everything squared. So one more time, what is the difference quotient? Now we know that the difference quotient is the average rate of change of any function between 2 points. Okay, that's the average rate of change. So now this doesn't completely solve our problem. How do I get this? The slope of this line here at this point, or the tangent line. Okay, here's our next assessment.
Did you say that?
Yes.
Quotient is the average rate of change?
Yes. So the difference quotient is the, let me write it. So this is nothing else but the difference quotient. Can I abbreviate DQ? Okay. So the average rate of change is the difference quotient. So it's the average rate of change of any function between 2 points. Average rate of change of any function between 2 points. As you saw, we had a point, we created another one, and we determined the slope of the secant line, or the average rate of change between 2 points. So now, here's what I'm going to do, and you'll tell me if you agree with this. Here it is. As x plus h gets closer and closer to x, or, in other words, as h approaches or gets closer and closer to awesome, right? As x plus h gets closer and closer to x, then h is shrinking to 0, right? There is no other way. So as this gets closer and closer to this, obviously h gets closer and closer to 0. Agreed? Okay. The slope of the secant line gets closer and closer, closer and closer. I'm not saying equal. I'm saying I'm using an arrow. I'm not using the equal symbol. So as x plus h gets closer and closer to x, which really means as q gets closer and closer to p, in other words, the slope of the secant line, or I could also say the secant line becomes or gets closer and closer to the tangent line. So the slope of the secant line gets closer and closer. It's an arrow. It doesn't say equal. Gets closer and closer to the slope of the. So this is all in motion, however, as you've noticed. I cannot determine the slope of the tangent line without saying as x gets closer and closer, or as h gets closer and closer to 0, the slope of the secant line will get closer and closer to the slope of the tangent line. So that's how we determine the slope at this point. In motion. And that's the concept of the limit, because that's what the limit is. As h approaches 0, the slope of the secant line will get closer and closer to the slope of the tangent line. So now here's a question for you. What will happen here if I say it's the difference quotient, it's the slope of the secant line? And now I'm telling you, and it's a contradiction, right? It appears to be a contradiction. I'm telling you, h approaches 0, this will become the slope of the tangent line. But can I make h 0?
No.
But I never said equal. I said h gets closer and closer to 0. I never said h is 0. I said as h gets closer and closer to 0, the slope of the secant line will become this, or get closer and closer to the slope of the tangent line. So always remember, because this is part of limits, when we say h approaches 0, we really mean h does not equal 0. It's completely understood. When we say h approaches 0, I really mean it. I'm not saying h is 0. Quite the contrary, I'm saying h is not 0, because I cannot plug 0 in here. So now I still have 6 minutes. I would like you to choose any function you want for which we should determine the difference quotient, because it's super important and I need to practice with another function. Now here's a question for you before you pick a problem. It can be any function. It can be rational. We already did a rational. It can be radical. It can be polynomial. It can be anything you want. So, but here's one question for you. Here's our function again. So at this point, this slope, the slope of this line, will give us, bless you, will give us the, bless you, the rate of change of the function at that point. At this point, the slope of this line will give us the rate of change of that function at that point. Here, the slope of this line will give us the rate of change at that point, and so on and so forth. So what concept is this? For this x value, a number, which is the slope. For this x value, another number, which is the slope. For this x value, another number, which is the slope. For this x value, another number, which is the slope, and I can continue forever. What am I creating here? I'm creating an input and an output. What am I creating? A? Yes, which is a function. I'm creating the function. So when we put all these together, that function that we create, which will be called the derivative, will give us the rate of change, the slope of the tangent line at any point we want. Under conditions. The function is to be continuous, differentiable, blah, 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 blah. But all these rates of changes are input x, give you another value. You give me an x, I'll give you the slope. You give me another x, I'll give you the slope. You give me another x, I'll give you the slope. This is the concept of a function. We are creating a function that will give us the slope of the tangent line to the graph of f of x at any point where the function, I'll tell you the conditions later. So give me any function you would like to find the difference quotient for. I know you're tired, so let's say 2x plus 1. So for the square root of 2x plus 1, we want to determine the difference quotient. Now, I'm hoping that moving forward, you will always remember. In pre-calculus, I said to my students, it's okay if you don't remember the difference quotient. But now we have no reason why not. Well, we have no excuse why not to remember it. What was it? F of x plus h minus over h. Awesome. So I have the difference quotient, which is f of x plus h minus f of x divided by h. You will see this the entire semester. This difference quotient into all sorts of different forms. This will be the derivative. This will be the function that determines the slope everywhere. Okay, so this I have, sort of, but what I don't have is this. That's the only one I have to work on. So please dictate. Right, so I'm going to write already distributed, plus 1, minus the square root of 2x plus 1 divided by h. let me remind you what happened when we determined the first difference quotient. What happened? Two things happened. Number one, all terms without h at the top went away, canceled. Awesome. So always remember that. All terms without h must go away. What is the second thing that happened? Exactly. Went away. Because I have to make it 0. And if it's still there, I can't make it 0. So, okay, so how do we address this? How do we handle something like this? If we want to simplify it, what is the only way for radical functions? Okay, I have $10 in my pocket, I'm going to square it. I just choose to square. I can't. If it's not an equation, I cannot square. If you say x equals 2 and you say square both sides, I agree. Because you are creating sort of, not entirely, an equivalent equation to the previous one. But you cannot say, just say, here's a fraction, 1/2. Square it, it's going to be equal to 1/4. No. So what can we do?
Multiply by square.
By? What is it called?
The reciprocal.
Exactly. Right. So it's the conjugate.
Right, okay.
The conjugate. Please remember this. This is going to follow us throughout the entire semester with limits. Being able to simplify something like this. I don't have enough room there, so I'm going to write it multiplied here. So the square root of 2x plus 2h plus 1 plus the square root of 2x plus 1 over the same thing. So see, I'm allowed to multiply top and bottom by the same quantity because I'm multiplying by 1. But I can't say 1/2 squared, okay, it's going to be 1/4, right? Equations, yes, we have to square them. Okay, so what do I get? Do not do anything to the bottom. You cannot even do anything, but just do not distribute h, just copy them. So don't forget what you wanted to say. Hold on, I just want to copy the denominator. Sorry about that. Yes?
It's not supposed to be the opposite. For
It's the conjugate. Okay, let me write this down for you. A plus b and a minus b are conjugates. So you thought, why did we need whatever we did at the beginning? Here's why. See it here? That's what I need. Good. So tell me about the top.
Well, you want to add them all together.
So it's a minus b times a plus b. A plus b times a minus b, or a minus b times a plus b. I want this.
No, wait.
That's true. It's squared, but I already did.
Oh, okay, because you, right.
Minus. Careful, we are distributing negative. Yes. Be very careful, we are distributing the negative 1. Good. What happens next? What did we say? One thing mandatory.
Get rid of
Terms that do not have h must disappear, must go away. Here they are. Nicely. Careful, if you do not change the sign as you are supposed to, those terms will not go away. Okay, so then what is left at the top? I don't want you to simplify in a sum like that. I know it's cumbersome to write it one more time, but I recommend it. Then simplify, and then we get this. Nobody can read that. I just don't want to go over. It's 53, and I want to finish with one thought here. So, what is this? Can anyone express the meaning of this? Or tell us what is the meaning of this for the function that we picked? It gives the rate of, not yet, you're close. It gives the rate of change for this function between 2 points. So it gives you between 2 points. Now, can you tell me what will be the instantaneous velocity as age approaches? In other words, as q gets closer and closer to p, in other words, age approaches 0, what will this approach? I covered exactly what goes away. Nothing else goes away. We are only talking about age approaches 0. So when I want to move q closer and closer to p, age shrinks closer and closer to 0. That's the only change. X does not change, the function doesn't change, just age changes. So what will be the answer when we make h get closer and closer to 0? See, this is not the equal symbol, and this is not the equal symbol. I'm not making h 0. I'm saying when h gets closer and closer to 0, what is the final answer? 2 over,
2x plus 2 times.
these are the same,
2x plus 1, 2.
so this will be 2 over twice the square root of 2x plus 1. This will go away, so this will be 1 over the square root of 2x plus 1. This is the function that will give us the slope of the tangent line to the square root of 2x plus 1 at any point where the function exists as this continuous differentiable, blah, 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 blah. This will be the function that I just gave you an example of. Any questions?